Okay, good morning. Sorry, I was going to start, then something happened, then I have to go and settle. Okay, come. How are you this morning? Good. Okay. Okay, so this is what we will do this morning. Yesterday we already covered the speed time graph. Today we're going, sorry, we didn't do speed time. Yes, so yesterday we did distance time graph. Today we're going to learn about the speed time graph. Then after that, I want you to just try some questions. It's only 2 questions. Where is it? 2 questions about but A, B, C, D, E, F lah. It's the graph. There are graph questions, but need you to try because it's like you need to know, you need to get some practice on how to interpret. Then I will also we try these questions first. Then after that, maybe we'll do a few more questions. We'll see how it goes lah. Okay, see how's your understanding. If you can do these 2 very well, then then maybe we can move on. Okay, am I sharing my screen? No, I'm not. All right, so yesterday we already learned up to here distance time graph, and we already learned also. I mean, we also did learn. We recalled how to learn. What am I saying? So yesterday we learned about distance time graph. We recalled how to calculate gradients, and we can also see. Based on the way we calculate gradients, we compare the formula to speed. We found that it's the same. So that's why the gradient for a distance time graph is the speed. So today we're going to look at speed time graphs. So when you write like that, remember that the first word will be on the y-axis and the second word will be on the x-axis. Here. Okay. So this would be with my. Okay. So this would be speed, meters per second, and this would be time in second. Can also be kilometers per hour lah, or an hour. That depends on the question. So anyway. So the difference here is that when we compare speed time to distance time, so remember that distance time refers to the starting point or the original point of comparison, and then we see how far the object is as time passes from this original point. But a speed time graph shows us how fast the object is moving along the way. So it's not how far now, it's how fast. So I want you to think logically. Now you think this is speed. This is showing us speed. So if we have a graph like this, this blue color line, do you think the object is moving or not moving? What do you think? So I'm going to take a photo. I'm taking a photo to put on the Jamboard later. Okay, what do you think? Look at the blue line. No. Okay. Why? So correct. Why do you say it's not moving? Why is it that you say it's not moving? Like, what is the evidence? So when I ask for evidence, because in science, right, like sometimes you make a conclusion which is correct, but sometimes you need to prove. Sometimes, because in the exam question, sometimes I can ask you, like, what is the reason? Explain. So from this graph, why is it that you say it is not moving? What is the evidence? What is the evidence? Do you understand the question, or you don't know how to give the evidence? Stationary. Now, stationary means not moving. Already we know it's not moving. But what is the proof? What is the proof that it's not moving? It's because it's zero, ma? Because the speed is zero, right? It's along here, speed is zero. That's your proof. Do you understand? The speed along here is zero, right? What if we have a graph like this? Moving or not moving? You sure? You look now, this is speed time graph, you know. Imagine got a number here. Let's say the number here is 10. Does that mean it's not moving? It's moving, right? Moving with what? Constant or changing speed? What do you think? Constant or changing speed? Not sure. You see the number is 10 all the time, as time passes. So you have to learn how to interpret the graph like that. This is time graph. So it means you imagine time is 1, time 0, 1, 2, 3, 4, 5. All the time, the speed is 10. No matter what the time is, the speed is 10. So that's how you have to interpret the graph. You must see, like, I mean, you need to get used to it lah. So you see, when the time is passing by, you see, no matter what the time, you try to put whatever the time at 100 seconds, time at, imagine far in the future, 1,000 years or so, it's still 10. So it's moving at constant speed. Huh? Wait, does that make sense? I'm just going to fix this. Okay, so that's how you interpret. And this, when I mean by interpretation, is because there's some questions where they give you the graph and they ask you to describe. So to describe means like that, moving with constant speed, or is it stationary? Okay. Let's say, so the number is not important. Okay, so let's say now we have this kind of graph, like this. So this graph now is showing a line going up. So do you think this for this particular object, do you think it's moving or not moving? What do you think? Moving. Okay. How about the speed? Is it constant or is it changing? Changing. Okay. So how's the change? Is the change increasing speed or decreasing speed? What do you think? Correct. Good. If we have this kind of graph, what do you think? Correct. Yes, you are getting the hang of it already. Okay. So there's some additional information like the gradient concept, like for gradient for speed time graph and all that, right? Sorry, like the gradient for distance time graph, we know gradient is speed. So like yesterday you asked me, is this gradient speed thing only for distance time graph? Yeah, it's only for distance time graph. If we have a speed time graph, the gradient is something else already. So we'll go through that now. Let me just load the image from the book. Okay, I will need to explain first though, because oh yeah, it's not that clear. Okay, just the two blue color one. All this all no need, but the blue color one. So cars traveling at steady speed. In the book they wrote steady, but it's the same meaning as constant. Okay, constant and steady, same meaning. Okay, same meaning. So that you can see from here, if it's a straight line like this, it's constant speed. So this one is E, right? So this one is actually same as E. And then this one is going up. So this one is F. But I gave you this additional tool because you also need to learn how to interpret. The book didn't give lah, but they kind of give in exam. They, this kind of red color or blue color kind of graph. In fact, the question also got. Anyway, so let's talk about the gradient. So I'm going to another slide just to show you. If let's say we have a speed time graph, let's take no lah, if I take that, it's what gradient to count. Let's say you have, sorry, a graph like that. Okay, doesn't matter the shape. It doesn't matter the shape. But you just need to remember this, that gradient, if you remember, is what the y2 minus y1 over x2 minus x1, or I call it rise over run. Or you can also call it like a change in y over change in x. So again, like how you figure out what the gradient represents, you can use the gradient formula. So change in y over change in x. But remember that for physics, we don't call it y and x. This is speed and this is time. This is y-axis lah, y-axis, x-axis. But the y-axis is speed, x-axis is time. So then when we look at this speed time graph, it's different from distance time already, obviously, because it's speed ma, hello, right? So gradient, when you look at this, it becomes speed divided by time. Okay, so your syllabus, I find it a bit confusing because sometimes they put speed time, sometimes they put velocity time. We will look at other graphs shortly, but just to show you, you calculated acceleration here. So acceleration, right, is when there's a change in velocity. Like when there's acceleration, velocity increasing, acceleration, there's deceleration, sorry, velocity is decreasing. And we know acceleration is change in velocity over time. Now, by right, I don't know why this, your syllabus, right, is sometimes they put speed time, sometimes they put velocity time, but never mind. Basically, you just think of it as this is the scalar version, right, of speed and time. If there's a change in speed, it's actually accelerating. For now, you think of it like that. Because now it's increasing speed, when we say accelerate, when something accelerate means it's getting faster. So when the speed is increasing means there is acceleration. That's why acceleration is the same as gradient. Because if the speed is increasing, means it's accelerating. So when the speed, here's acceleration. Here the speed is decreasing, so there's deceleration. So that's why acceleration is equal to the gradient. Can follow? Can, okay. So that's one. Now, another thing you need to know, this time, got extra bit, area under the graph. So when we say area under the graph, how you do area under the graph is, depends, they will ask you which section. So that means, let's say, for example, they mark, okay, I want this section to this section. Let's say A to B. So from point A to point B, you must drop until the x-axis. It's until x-axis. Definitely until x-axis. Then, area on the graph, you draw straight line from the 2 points, go down to x-axis. Then, you calculate the area under the graph. So you see the shape here. This is a parallelogram, right? So you count the area of the parallelogram. Or another way is you can count area of the triangle plus area of rectangle. It doesn't matter. You'll get the same answer. So area under the graph depends on the shape. Depends on the shape. Because if you get another shape like this, like let's say you get this kind of shape, then there's rectangle. Because it's like, what's this? Then you see, let's say we take the whole thing, let's say. Also can, like let's say, like depends on the question, they ask you count the thing. Then this one is you can see, it's a rectangle shape. Then you count the area as a rectangle, you take the length times the height. So area under the graph depends on the shape. So you see from the graph, you have the two, they will give you they'll tell you which point, then you drop to x-axis, then you count the area under the graph to the x-axis. That's what you mean by area. So when you count the area, it's like for what? Why we count the area for what? Means what? Means this. I'll take the rectangle to show you the relationship. So you can see here the area of the rectangle. Look at that rectangle first. This line, you see from start to finish, it's like the same amount of time. Then here, this line from start to finish is actually what? Speed. So it's time times speed. Then if you recall, the speed formula is distance divided by time. You rewrite this, you will get distance, you bring this up, time times speed. Same, right? That's why if you count area under the graph, it's actually the same as the distance. Can follow? Still can. Okay, good. Got a few more things. Okay, so we learned distance time graph. We learned speed time graph. Actually, right, because beginning of this chapter, you also learned about vectors, right? Remember we learned all that complicated stuff about what's this displacement velocity. Actually, right, so you also need to learn displacement time and velocity time graph because we learned distance time graph already. Now we've learned speed time graph. Okay, but you also need to learn displacement time and velocity time, but it's not difficult. Once you know distance time graph and speed time graph, once you know this already, displacement time, velocity time, exactly the same. It's very, very easy. It's very, very easy. So just to show you the difference, basically, if you have a distance time graph, just to compare. Apa ni? Displacement time graph. Actually, they are almost the same concept. The only difference is that you must remember, oh, distance is scalar, no direction. Displacement is vector, got direction. So distance time graph and the displacement time graph, the concept is the same. Distance time shows you how far is the object from the original point. Displacement time shows you how far the displacement is from the original point. So it's also still meters. And time is also second. This one displacement is also meters. And time is second. Actually, so the only difference is that this one is showing distance, the direction don't care. Displacement is vector. So it actually doesn't, it's actually almost the different, I mean, like basically is, how to explain? Distance, right? It's just showing you how far is the object from the original position. Displacement is showing you the displacement. Like let's say that triangle concept, right? Triangle concept. What am I saying? What's teacher saying? Like you travel from your house to another house to the mall. Okay. So distance is just showing you you're traveling far away. Displacement it means it's showing you the displacement. Like you can actually come back to zero. Distance, no, distance will just keep going higher and higher. Anyway, don't worry so much about this. I will get you some IGCSE questions to do. For now, right, you just focus how to learn to calculate the gradient and all that. So we know that for distance time graph, the gradient is the same as the speed. Because why? Because gradient is rise over run, ma. Maybe I write again properly. Gradient is rise over run. Rise is what? Distance. And run is time. So that's why end up speed is also the same as gradient. And if you look at the unit, see, distance is meters, times is second. So then you count meters per second, same as speed, meters per second. Now, because distance time is, the speed is the gradient, that means now you think, then if you count the gradient for displacement time, which is rise over run, also, rise this time is displacement. And run is time. Also meters per second. But meters per second this time is not speed. Why? Because it's displacement. So if you look back at what we learned about speed and velocity, speed is distance over time, velocity is displacement over time. So that's why if you are looking at a displacement time graph, now this one becomes velocity. So different graph got different meaning, the gradient and all that. So why I'm showing you this is because I just want you to be aware that different graph, the gradient got different meaning. Okay. Can follow or not? Can. Okay, good. And then same thing with the speed time. This one is a bit, actually, I don't know why your syllabus do like that. I find they like to confuse the students because the other syllabus I teach, SPM syllabus, is more straightforward actually. But never mind, don't want to talk so much. Okay, anyway. So if you have a speed time graph, and a velocity time graph, same concept also. Now velocity is meters per second, speed is also meters per second, and this one is time. Now whichever the case is, right, whatever the graph shape, doesn't matter. When you calculate gradient, remember gradient is rise over run. This becomes speed over time. And then just now we already saw that, yeah, because increasing speed means acceleration is the gradient. No? What color I use just now? Okay, maintain. I just want to maintain the same color. Acceleration is the gradient. Okay. But actually, right, acceleration is more suitable for velocity, because if you calculate gradient here, the gradient is also rise over run. And this is what, you see the rise is what, velocity, ma? And the run is what, time. Acceleration formula, if you remember, you did the calculations, right, for the earlier topic. Acceleration is change in velocity over time. So the acceleration is actually the gradient also. So in your syllabus, you learn whether it's speed time or velocity time, the acceleration is the gradient, because I think because there's no scalar option. Like here, distance is scalar, speed is scalar. Displacement is vector, velocity is vector. But acceleration, there is no scalar version. There's only acceleration. There's no like, oh, acceleration scalar type and vector type. No, it's just acceleration. Acceleration is really a vector. So that's why in your syllabus you learn whether it's speed time or velocity time, when you count acceleration, is for both speed or velocity. Just to show you the unit, this one is meters per second divided by second, actually becomes meters per second squared. Meters per second, another way to say it. So this is meters per second divided by second, this becomes meters per second squared. The other one is area. Area under the graph, just now we saw is speed times time. Well, time times speed lah. So if these two you times together, time times speed, that's why you get distance is the same as the area under the graph. So if you take the same concept and you apply to the velocity time graph, it becomes time times velocity. Then if you remember, velocity is displacement over time. Velocity is displacement over time. So you bring up, you get displacement equals velocity times time. That's why displacement is the velocity, because it displaces velocity. Sorry, what am I saying? Displacement is the area under the graph. Because the vector, scalar, scalar. Can follow? You think can? Okay. It's quite a lot of information today. We stop here first. We won't push on. Okay, see you. Bye.